73% of RAG failure happens before the LLMs even sees the question. If you are a backend or distributed system engineer, RAG is probably the fastest way to become relevant in the AI infrastructure. So here is the thing. LLMs are really smart, but they have a big problem. They make stuff up. They confidently tell you things that sound right, but are completely wrong. This is called hallucination. And it happens because the model is generating text based on patterns it learned during training, not by looking up actual facts. On top of that, LLMs have a knowledge cutoff. They do not know anything that happened after their training data was collected. And they definitely do not know your company's internal document, your product catalog, or your customer records. Think about it like this. Imagine you hired the smartest person in the world, but they have never read any of your company's document. You ask them a question about your refund policy, and instead of saying, "I do not know," they just make up an answer that sounds reasonable. That is what LLM does without RAG. RAG fixes this. It gives the model a way to look things up before answering. And by the end of this video, you will understand exactly how to design RAG system from scratch. The ingestion pipeline, the retrieval pipeline, the failure points that break production systems, and the architecture that ties it all together. If you watched our earlier videos on LLM Inference and KV Cache, this is where we build on top of that. RAG sits in front of the LLM Inference service and feeds it the right context. Let us get into it. Before we build anything, let me address the obvious question. If the model does not know your data, why not just paste all your documents in the prompt? Some people actually try this. They take their entire knowledge base, maybe few hundred pages of documents, and shove it all into the context window. Modern models can handle 100,000 tokens or more. So technically it fits, but there is a catch. 3 catch actually. First, cost. Every token you send costs money. If you are stuffing 50,000 tokens of context into every single request, your API bill is going to be enormous. Multiply this by thousands of users and you have a serious problem. Second, speed. More input tokens means more processing time. The model has to read through all of the text before it can start generating an answer. And if you remember from our KV Cache video, all that context need to be stored in the KV Cache, which eats up GPU memory. Third, and this is the one that most people miss, quality actually gets worse. When you give a model too much context, it starts losing track of what is relevant. This is a well-studied phenomenon where models perform well on information at the beginning and end of the context, but struggle with stuff buried in the middle. And there is a performance cliff. Once you go past about 2500 tokens of retrieved context, accuracy starts to drop. So the naive approach does not work at scale. What you really want is a system that looks at user's question, finds just the relevant pieces of information, and feeds only those to the model. That is RAG, Retrieval-Augmented Generation. Retrieve first, then generate. Now here is where it gets interesting. Building RAG systems has completely 2 different pipelines. One runs offline to prepare your data. The other runs in real time when a user asks a question. Let me walk you through both. The first pipeline is the ingestion pipeline. This is where you take all your raw documents and prepare them so they can be searched quickly later. Think of it like building an index at the back of a textbook. The index does not contain the full content, but it tells you exactly where to find what you need. There are 4 steps: preprocessing, chunking, embedding, and storing. Let's discuss first step, preprocessing. Your documents come in all shapes and sizes: PDFs, Word document, HTML documents, Slack messages, database records, etc. Before you can do anything useful, you need to extract the actual text, strip out formatting, headers, footers, page numbers, remove boilerplate, normalize the text so it is clean and consistent. This sounds boring, but it matters a lot. The second step is chunking. Here is where things get interesting. You cannot feed an entire 50-page document into the system as one piece. You need to break it into smaller chunks. But how you break it up has a huge impact on how well your RAG system works. Let me give you an analogy. Imagine you are running a pizza delivery service and you need to cut each pizza into slices for each delivery. If you cut the slices too small, each slice is just a tiny bit of crust with barely any topping, not very useful on its own. If you cut them too big, they do not fit into the delivery box. And if you cut right through the middle of topping cluster, you ruin the experience. That is chunking. too small, and each chunk lacks enough context to be meaningful. Too big, and you are back to the problem of feeding the model too much irrelevant text. Cut in the wrong place, and you split a thought across two chunks, so neither one makes complete sense. There are 4 main strategies for chunking. Fixed size chunking just cuts every n tokens regardless of content. Simple, but it splits sentences and thoughts in half. Recursive chunking is smarter. It tries to split on paragraph breaks first, then sentences, then words. This is the most common default. Semantic chunking uses embeddings to detect when the topic changes and split there. And document-aware chunking uses the actual structure of the document, headers, sections, tables, to create meaningful chunks. The production sweet spot is around 400 to 512 tokens per chunk, with 10 to 20% overlap between consecutive chunks. That overlap is important. It means that if a thought spans 2 chunks, the second chunk still has some context from the first. One more advanced technique worth knowing is contextual chunking. The idea is that before you store a chunk, you prepend a short summary of the document it came from and where it sits in the document. So instead of chunk that says the return window is 30 days, you get a chunk that says from the customer service policy, section 3 returns, the return window is 30 days. This reduces retrieval failures by 35 to 49% because the chunk now carries its own context. Here is a question for you. You are building a RAG system for a legal firm. The documents are full of cross-references and individual paragraphs do not make sense without the surrounding context. Which chunking strategy will you pick and why? Drop your answers in the comment below. The third step is embeddings. Once you have your chunks, you need a way to search through them. And this is where embeddings come in. Think of an embedding as GPS coordinates for meaning. When you have a physical address, you convert it to latitude and longitude so you can calculate distances. Embeddings do the same thing for text. They take a chunk of text and convert it into a list of numbers, a vector, that captures what the text means. These vectors have a lot of dimensions. Modern embedding models produce vectors with 1024 or more dimensions. Each dimension captures some aspect of meaning. The result is that text with similar meaning ends up close together in this vector space, and text with different meaning ends up far apart. So how do I return a product, and what is your refund policy? Would have very similar vectors even though they use completely different words. One critical rule: you must use the same embedding model for your chunks and for user queries. If you embed your documents with one model and queries with a different one, the vectors live in a different spaces and nothing will match. This is surprisingly common production bug. The step 4 is storing. Once you have all your vectors, you store them in a vector database. This is a database that is specifically designed for similarity search. It stores both the vector and the original text chunk, so when you find a match, you can retrieve the actual content. That is the ingestion pipeline. Documents go in, searchable vectors come out. You run this offline whenever your data changes. Now let us talk about what happens when a user actually asks a question. This is the retrieval pipeline and it runs in real time. Here is the flow. The user sends a query. You embed that query using the same embedding model. Then you search the vector database for the chunks most similar to the query. You re-rank the results and then you take the top chunks and inject them into the prompt alongside the user's question. The LLM reads the context and generates a grounded answer. Let me break each step down. The first step is search, that is finding the right chunk. When your query vector hits the vector database, the database needs to find the most similar stored vectors. But here's the thing. You might have millions of chunks stored. Comparing your query against every single one would be way too slow. So vector databases use clever indexing algorithms. The most common one works by building a graph of vectors where similar ones are connected. Think of it like finding your friends in a huge stadium. Instead of checking every seat, you ask the person nearest to the entrance, "Do you know anyone who looks like my friend?" They point you to someone closer. That person points you to someone even closer. Within a few hops, you find your friend. That is roughly how these approximate search algorithms work. Now here is where it gets interesting. Semantic search using vectors is great at understanding meaning, but it has a blind spot. It struggles with exact matches. If someone searches for error code XJ4521, a semantic search might return result about error code in general, but miss the specific document that mentions XJ4521 by name. That is because the embedding captures the concept of error codes but loses the exact string. This is where hybrid search comes in, and in production, this is the standard approach. Hybrid search combines two approaches. Dense search uses embeddings for semantic similarity. It understands meaning. Sparse search uses traditional keyword matching. It finds exact terms. You run both searches in parallel, then combine the results using a technique called reciprocal rank fusion. This merges the two ranked lists into one, giving you the best of both worlds. The recommended approach in production is usually retrieve the top 50 candidates using hybrid search. But here's the thing. Those top 50 results are not in the best order yet. The initial search is fast but rough. Re-ranking takes those candidates and uses a more sophisticated model to score how relevant each one is actually to the query. Think of it as a two-stage hiring process. The first pass quickly scans resumes for keywords. That is the initial retrieval. The second pass carefully reads the shortlisted resumes. That is the re-ranker. Re-ranking adds about 200 to 400 milliseconds of latency, but it improves result quality by 15 to 30%. After re-ranking, you take the top 5 chunks and pass those to the LLM. Quick question here. Your RAG system latency budget is 500 milliseconds total. Naive retrieval takes around 200 milliseconds. Hybrid search with re-ranking takes around 400 milliseconds. But the re-ranker improves quality by 25%. Which do you pick? And what else could you do to make the re-ranker fit in the budget? Let me know in the comments below. So the full retrieval flow is query comes in, embed it, run hybrid search to get top 50, re-rank to get top 5, inject those 5 chunks into the prompt and send it to the LLM. The model reads the retrieved context and generates an answer that is grounded in your actual data. The total latency of this pipeline is typically around 400 milliseconds for the retrieval part, plus whatever the LLM takes to generate the response. Now we have the full picture. The ingestion pipeline and the retrieval pipeline. It sounds clean, right? But here is where it gets real. Production RAG systems fail all the time, and most of the failures are not where you would expect. Remember that number from the beginning. 73% of RAG failures are retrieval failures. That means the problem is usually not the LLM generating the answer. The problem is the right information never made it to the LLM in the first place. Let me walk you through the most common failure points. Bad chunking is the number one cause. If your chunks are too small, they do not carry enough meaning for the embedding models to understand them. If they are too big, the embedding tries to summarize too much and the meaning gets diluted. And if you split right in the middle of an important thought, neither chunk makes full sense. Semantic gap is when the user asks a question using completely different words than what is in the document. A customer says, "My widget is not working," but the documentation says, "Troubleshooting device malfunction." The embeddings might not connect these two phrasings. Still, embeddings happen when you update your documents but forget to rerun the embedding pipeline. The vector database still has the old versions. The system retrieves outdated information and the LLM generates an answer based on data that is no longer accurate. Context overflow is when you try to pass too many chunks to the LLM. There is a sweet spot. Beyond about 2500 tokens of retrieved context, accuracy starts to drop. More context is not always better. Exact match failure is why you need a hybrid search. Pure semantic search misses product IDs, error codes, and specific names. An embedding model mismatch. Using one model to embed your documents and a different one for queries means the vector lives in completely different mathematical spaces. Nothing matches properly. Here is the important takeaway. When your RAG system gives a bad answer, most teams immediately blame the LLM. But the real fix is almost always in the retrieval layer. Better chunking, better search, or better re-ranking. Now let me put the entire system together so you can see how all the pieces connect. On top, you have the ingestion pipeline running offline. Documents go through preprocessing, chunking, embedding, and get stored in the vector database. On the bottom, you have the retrieval pipeline running in real time. User query gets embedded, hybrid search finds the top 50 candidates, the re-ranker narrows it to the top 5, and those get injected into the LLM prompt. Notice how this connects to the rest of the series. RAG sits in front of the inference service we discussed in our previous video. It adds retrieved context to the prompt, which means more input tokens for the LLM to process. That retrieved context also increases the KV cache size. The model needs to store attention states for all those extra tokens. And in the next video, we will look at how RAG is both a cost problem because you are sending more tokens and a cost solution because it is much cheaper than fine-tuning a model on your data. Here is one more question. Your RAG system is live and working, but the users are complaining that it gives outdated answers. The engineering team says the documents are up to date. Where would you look first to diagnose the problem? Think about what we just covered and drop your answer below in the comments. Now let us talk about how this shows up in the system design interviews. The topic question sounds like this. Design a system where user can ask questions about a large document collection and get accurate answers. Here is what a strong answer looks like versus a weak one. A weak answer jumps right to we use a vector database and an LLM. That is like saying we use a database and a server. It is too vague to demonstrate any real understanding. Another weak move is focusing only on the LLM part and ignoring retrieval entirely. A strong answer starts by clarifying the requirements. How large is the document collection? How often does it change? What is the latency target? What types of questions will users ask? Broad summaries or specific lookups. Then you walk through the architecture methodically. You explain the ingestion pipeline, preprocessing, chunking strategy with a rationale for the chunk size you choose, embedding model choice, and vector storage. You explain the retrieval pipeline, hybrid search with dense and sparse re-ranking, and how many chunks get passed to the LLM. And you discuss trade-offs at each step. Common mistakes interviewers sees includes number 1, ignoring chunking entirely. If you do not discuss how documents get broken up, you are missing the component that caused 73% of failures. Second, skipping re-ranking. Going from raw vector search results straight to the LLM means you are feeding potentially low quality results into your prompt. Third, not discussing hybrid search. Pure semantic search has well-known blind spots for exact matches. Fourth, forgetting about data freshness. If the interviewer asks, what happens when a document is updated and you do not have an answer, that is a red flag. And fifth, not mentioning the connection between RAG and the rest of the serving infrastructure. RAG increases token count, which increases KV cache usage, which increases cost. A strong candidate connects these dots. Strongest candidates also mention latency trade-offs. Naive RAG runs around 200 milliseconds for retrieval. Hybrid search with re-ranking takes about 400 milliseconds. Agentic RAG, where the system decides whether to do one retrieval or multiple, can take 2 to 8 seconds. Knowing these numbers shows you have production experience or at least production awareness. So that is RAG from scratch. The key takeaway is RAG is not just search plus LLMs. It is carefully designed system where every component, chunking, embedding, search strategy, re-ranking affects the quality of the final answer. In our next video, we are going to tackle a topic that is directly connected. How to cut your LLM cost by 80%. Because RAG adds token to your prompt and those tokens cost money, we will look at 6 different techniques to bring down that cost, including some that directly build on what we learned today. If you like this video, please hit the like button and subscribe to this channel so you do not miss the rest of the series. And if you have any questions about building RAG systems, drop them in the comments below. See you in the next one.